A conceptual look at dielectrics. In an earlier video, we stated that anytime you add a dielectric between the plates of a capacitor that didn't originally have one, aside from air, that the capacitance goes up. And we're going to try to conceptually prove that to you in this video. Here we look at what happens when we insert a dielectric between a capacitor's plates. Follow the logic here. First, we charge a dielectricless capacitor of capacitance C using a battery of voltage V. By dielectricless, we mean that the capacitor at the moment has no dielectric aside from air or a vacuum. After charging, the capacitor has charge Q on its plates and a voltage V and an electric field E between plates. Then, while leaving the capacitor connected to the battery, that's an important point for this first part, we insert a dielectric between the plates. So what's going to happen? Because the capacitor is still connected to the battery, V is constant. Aside from momentary fluctuations, and because the equation V equals ED holds true here, E is thus also still the same as before. If V is the same, we haven't changed the distance between the plates, therefore E must stay the same. Due to the capacitor's original electric field, the dielectric molecules become polarized. Now let's use this little picture over here on the right side of the screen and see if we can make that clear to you. I've blown this space up between the capacitor plates nice and big so we can draw some things there. Let's say that this is the plate that has the positive Q, and this is the plate that has the negative Q. Therefore, we know that the electric field lines are going to point that way. Then we put a dielectric in here. There's a dielectric molecule. There's a dielectric molecule. I'm drawing these dielectric molecules obviously way bigger than they are. But that's a dielectric molecule, and you remember that a dielectric is an insulator. And because it's an insulator, these electrons in each molecule can't leave the molecule, but they can shift to a different position. And so based on this electric field, positive charges would tend to go with the field. Well, the protons in here can't really move too much. They are relatively fixed in place, but the electron clouds can shift a bit, and electrons, negative charges, go opposite electric fields. So what you end up with is a charge distribution in each of these molecules that goes something like this, with the negative on the top here as I've drawn it and the positive at the bottom. Now, what that does is, this is the next sentence, the resulting charge shifting within the dielectric molecules induces more charge to accumulate on each of the two plates. See, before we put the dielectric in there, there was a certain amount of interaction between, these positive charges up here on this plate and these negative charges on this plate here. But when we put a dielectric in, now there's a negative charge, and man, it's really close to that top surface. So you know what happens? I know this is conventional charge, but we might say that attracts more positive charge to that plate. And then the same thing happens down here. You see that positive charge, ooh, that's going to attract some negatives. So you end up with more charge than you did. You started with a certain amount of charge, and now when you put that dielectric in there, now you got more. All right. And this can happen. We can move more charge because the capacitor is still connected to the circuit, right? It's still a complete circuit with the battery hooked up. So charge can still move for a short time. So what has happened to the capacitance? The definition of capacitance is this equation, Q over V. We've gone through that several times. And our new capacitance is found from the larger Q. See, now there's more charge. We just said that. And the voltage was the same as it was before. So what has that done to the capacitance? If Q is bigger and V is the same, then the capacitance has increased. It's gotten bigger. You see that? We put a dielectric in there, and the capacitance went up. Now, let's do the same thing. charging up the capacitor without a dielectric, except this time we disconnect the capacitor from the battery before we insert the dielectric. In the first case, we left the battery hooked in and put the dielectric in. Now we're going to charge up the capacitor, we're going to unhook it from the battery, and now we're going to slide that dielectric in. What happens? Now, because the capacitor's plates have been isolated from the rest of the circuit, Q is constant. There's a certain amount of charge, if we're going to use our picture here on the right, there's a certain amount of charge on each plate, and that can't change now. As before, due to the capacitor's original electric field, let me draw one electric field line in there. That's the original electric field. The dielectric molecules become polarized. Let me draw a couple of dielectric molecules in here, blow them up nice and big so we can see them. Once again, the electron clouds are going to shift so that we're going to have some kind of charge distribution within each of those dielectric molecules that looks like that. Before, when the capacitor was still hooked up to the battery, that induced more charge to accumulate on the plates, but now that can't happen because the capacitor has been isolated. So that's what it says right here. But unlike before, no more Q can accumulate on the isolated plates. The polarized dielectric molecules produce their own electric field, which points opposite to the plate's original one. Look at each of these dielectric molecules. Can you imagine a little electric field within this molecule? And which way would it point? Wouldn't it point up? Wouldn't the little electric field within this dielectric molecule point up? Wouldn't the little electric field within that dielectric molecule point up? Because electric field lines point away from positive charges and towards negative charges. These little dielectric electric fields are pointing opposite this one. The net electric field between the plates has thus decreased. The net electric field is the original one plus the electric field that's within the dielectric here. This happened in the first case too, for your information. But in that case, the added charge that rushed onto the plates quickly brought the net electric field back up to its original strength. So that did happen in the first case, but more charge rushed onto the plates, and what ended up happening is the final electric field was the same as the original. Again, from V equals E times D, we see that now, if E has decreased, then V must also decrease, because the separation hasn't changed. So if E is smaller, then V is also smaller. So what's happened to the capacitance? The new value is found from the same size Q, right? The charge didn't change, but the voltage is smaller. And what's the equation? Let me scribble it here one more time. Capacitance is Q over V. And if Q is the same size, but V is smaller than before, what happened to the capacitance? It's increased. So no matter which way you cut it, if you add a dielectric in to a capacitor, the dielectric is going to increase the capacitance.